Hi everyone, welcome back to Math 111. This is Scott. Let's get started. Today we're going to be talking about section 5.2. So you'll notice that we are not covering section 5.1 this class. It covers quadratics, which is a subject that is actually covered in Math 95 and actually to some extent in Math 65 as well. So what we are going to be talking about here in section 5.2 are what are called power functions and polynomial functions. Power functions and polynomial functions. So starting first with power functions, let's just say what they even are. So power functions, their format is this. You have f of x equals, and then what you can have here are things like a coefficient in front and an x to some power. So this is some number. This is some number. And so what you have is x to a power. So this does not include numbers to the power of x. It does not include multiple term expressions. It is purely of this form where you have something times x to a power. So this does not include. Does not include things with x's in the exponent. We'll see later in this term, those are called something else. Or expressions with multiple terms. But it does include some things that don't look like they're of this format, but with some amount of algebra you can put them into that format. However, any expression that you can use algebra to put into this form would qualify. For example, so here are some examples of functions that don't look like that, but nonetheless fit the bill. So for example, if we had f of x equals square root of x. So that doesn't appear to be of this form, however, we can rewrite this so that it's a 1/2 power, and then it qualifies. Another example would be something like, what if we had g of x is equal to 1 over x? Well, that can be rewritten as x to the negative 1, so the reciprocal function also would qualify. And then if we had something like h of x which equals, let's say, just the number 3. Well, that doesn't quite look like a power function. However, we could rewrite that as 3x to the 0, because x to the 0 just equals 1. So here we could insert that as necessary, and we could consider this one also to be a power function. However, something like f of x equals x plus 1. Not a power function. G of x equals 2 to the x. Not a power function. Or let's say something like h of x is equal to x plus 1 over x minus 1. Not a power function either. Alright, so power functions are one thing, and the important thing about power functions, as far as we're concerned here, is what certain of their graphs are going to look like in profile. So graphs of power functions. There are two pieces to a power function. There's the coefficient in front, and there's the power a. So the way the graph is going to look is going to depend on that. So the things it depends on. So for a, how the graph depends on a is based on whether it's positive or negative. So if a is positive, the graph will be oriented as usual. However, if a is negative, it will be upside down. It will be flipped. Upside down. So that's the importance of the A. It will tell you if you have regular orientation or upside down. Now as for the P, we have several possible things to consider. So if P is a positive integer, so by positive integer I mean a whole number and not negative. A whole number, not negative. Then the graph will resemble resemble the square or the quadratic graph. Y equals x squared if p is even and it will resemble the cubic graph y equals x cubed if p is odd. So for example, let's say we had f of x equals -2, so that's going to be the coefficient, x to the power of 5. So the power here is positive, that's the important thing, and it is an integer. It's not a fraction, it's not a decimal. And so what we have is an odd power with a negative coefficient. So it will resemble, generally speaking, the cubic. However, because of the negative in the coefficient, it's going to be upside down. So ordinary cubic is negative on the left, positive on the right. This will be the opposite of that. So it'll go like that. And if on the second case here we had something like g of x equals 2x to the fourth. Here we have a positive coefficient, so that means the orientation will be regular. And we have an even power, and that means it's going to look kind of like a quadratic. It's going to be going up and up on both sides. Okay. So that's the first case, if p is a positive integer. If p and I should say positive integer, we should say greater than 1. This is a special case. So a power of 1 just means it's actually just the identity function, f of x equals x. So if p is a negative integer, the graph will resemble either f of x equals 1 over x or 1 over x squared, depending on whether the power is even or odd. And then if p is not an integer, if p is a fraction, then you would have to figure out, based on what kind of root it was, what sort of power it would look like. So if p is a fraction, then the graph would be based, let's put it that way. on the equivalent root. Expression. Okay, so for example, if I had f of x, say this, example A, f of x equals x to the negative 3. So what we have here is a negative power, which is the same as 1 over x to the third, and this resembles the reciprocal function because it is an odd power. So it's going to be going like that. B, let's say g of x equals x to the 1/2 power. So then in that case, what we're going to be talking about is a square root. And from the toolkit, we know that that looks like that. Okay, that's all there is to say at this time about power functions. We'll revisit them a little bit later as we proceed along. But now we're going to talk about the other main category that this section is about, and that's polynomial functions. So polynomial functions. What these are made of are terms, each of which is a power function, each of whose powers is a non-negative integer. So the format for these is a sum of terms that are each power functions with non-negative integer exponents. So what that looks like is something like this. F of x is equal to, maybe you have 2/3 x to the 5th minus maybe 1/4 x to the 3rd plus x squared minus 0.1 x plus 2. But what you don't have here are any x's to any negative powers, or any x's in the denominator, or any x's to a fractional power. So the x's cannot be in the denominator. They cannot be raised to a fractional power or a negative power, that's the same as being in the denominator, or a decimal, which is the same as a fractional power. And they also cannot be in the exponent. So here what we have is a polynomial, and each of these are called the terms. So the pieces let's say separated by addition and subtraction are called terms. The exponent on x for each term is called the degree. So it's called its degree. The term with highest degree is called the leading term. It's called the leading term, and its coefficient is called the leading coefficient. And then finally, the degree of a polynomial is the degree of its leading term. And then one last thing, if necessary, you would have to multiply out some pieces in order to find the leading term. Note: if a polynomial is given in what is called factored form, which means a product of factors rather than a sum of terms, we would need to multiply it out to get the leading term. So for example, find the degree and leading term of the following. So first, let's just take something like this. Let's go with 2 minus 5x squared. So here, the leading term is the term with highest degree. Oops, 2 minus 5x squared. So the leading term is the term with highest degree, and that degree is the degree of the polynomial. So the degree here is 2, and the leading term would be the negative 5x squared. And for the record, then the leading coefficient, if you were asked that, would be just that negative 5. However, if what you saw was something like this, where you didn't have the terms all laid out like this, but you had instead something in factored form, you might be dealing with something like 2 plus x squared times 1 minus x, something like that. And maybe throw in one more x there. So then what you would have to do is you would have to actually multiply it out in order to find the leading term. So it's x times, and then you would just FOIL this part right here. So 2 times 1 is 2, 2 times negative x is minus 2x, x squared times 1 is plus x squared, minus, the last one is going to be x squared times x is x cubed. And then you would distribute the x through. 2x minus 2x squared plus x cubed minus x to the fourth. So there is our leading term. Even though it's written last, it's called the leading term. And the degree is its exponent. So the degree here is 4. The leading term is negative x to the fourth, and the leading coefficient is negative 1. If you don't see a visible number there, it's 1. And another way of thinking about coefficient is, what would you get in the leading term if you plugged in x equals 1? That's another way of expressing it. Now, the reason why we are interested in the leading terms of polynomials is that they have a big effect in the long run. So, end behavior. This refers to what happens to a function as x gets larger, either in a positive or a negative sense. So this is the behavior of a function's graph as x grows towards the positive or negative direction. So the way we write this, the way we write these things is we say, so we write x and then an arrow to infinity. This means x goes to the right, x approaches infinity. Or we write x approaches negative infinity to mean x goes left. Now for polynomials, what's going to be happening as x gets larger and larger and larger is that the y values themselves will also either be going up or going down. We'll see other kinds of functions later on that can do other things. And what we will be wanting to discover is what the end behavior is of the function as x goes in the rightward direction or in the leftward direction. So this is how we write the end behavior, and then the goal is going to be to figure out or to determine what happens to the output as x approaches, or as x goes each direction. And we write f of x goes to infinity, or f of x goes to negative infinity, depending on whether it's going up or going down. So y goes up, or y goes down. So here's the basic idea for how we're going to approach this in the case of polynomials. So here's the idea. The end behavior of a polynomial is determined by its leading term. So we're just going to have to look at the leading term, and then based on the graph of that, which will resemble a toolkit function, we can figure out what the leading or what the end behavior of the polynomial is going to be. Now here's it. Now there's a shortcut that we can use to find the leading term, and that is going to come in handy as the expressions that we're talking about get more complicated. So here is a shortcut for finding the leading term. For finding leading terms in factored form. Within each factor, we can ignore the terms of less than highest degree. So inside each factor, ignore the terms of less than highest degree. because these aren't going to end up contributing to the leading term if you FOIL it out. So for example, let's say we had something that looked pretty complicated. 3x squared minus x plus 1 times x minus 2 to the third power times 4x squared minus 5x cubed, something like that. So if we had something along these lines and we were actually going to try to multiply it all out to find the leading term, then that would be a big hassle because we would need to actually have 3 copies of this. We'd have to then multiply this all with the first copy, the whole result with the next copy, the whole result of that with the next copy, the whole result of that with this, and we'd have to carefully distribute everything with everything and then combine like terms. All that work just for one term, just for the leading term. And it's actually unnecessary, and what you can do is you can actually just say this, abbreviate it and say it just in the leading term. All that matters here is the highest degree term within each factor. So from the first factor, all that's really going to matter is the 3x squared. From the next factor, all that's going to matter is just the x. The minus 2 isn't going to affect anything, but that is raised to the third power. And then from this one, that term isn't going to be important, only this term will be. So it's going to be minus 5x cubed. And then you can just combine all of these. So you multiply together all the coefficients, and you would basically add together all the exponents. So this is going to be 3 times negative 5 is going to be negative 15. And then for the exponents, we have 2 x's next to 3 more x's next to another 3 x's for a grand total of 8 x's. So this is a shortcut for finding the leading terms if it's in factored form. Now let's actually put all of this to use to find the end behavior of certain functions, certain polynomial functions. So the task here is identify the end behavior. Alright, first let's take a relatively straightforward case, just something like this. F of x is equal to negative x to the 6th. So this is just a power function. It doesn't have multiple terms. So we don't even need to worry about identifying the leading term or anything like that. The leading term is identified for us. So the things that matter about this is the coefficient, positive or negative, is the power, even or odd. So the important thing is negative power, or negative coefficient, and even power. Which means that the graph of the function here is going to resemble x squared, however, it's going to be pointing down because of the negative. So what this means here is that as x goes to the right, it goes down, and as x goes to the left, it also goes down. So the way we can write that is f of x goes to negative infinity, that means down, as x goes to positive infinity, and f of x goes to negative infinity, that's again down, as x goes to negative infinity. So the hardest part about this is translating it into these hieroglyphics, which you just use f of x goes to positive infinity for up, negative infinity for down. And x goes to, you write positive infinity for right, negative infinity for left. Let's take, as a slightly more complicated example, something like this. G of x is equal to negative 5x to the 5th minus 2x squared plus x plus 1. So once again, all that matters about all of the terms is the leading term. And so the leading term is negative 5x to the 5th, which has negative power and an odd exponent. Now, because it has an odd exponent, it's going to look like a cube, but because it's a negative power, it's going to be like a cube that's upside down. So that means we've got one side up, one side down, and this is left and up. This is right and down, and that means that f of x, so starting with the right down, that goes to negative infinity as x goes to positive infinity. So this means down, this means right. And we can say f of x goes to positive infinity as x goes to negative infinity. Now let's try one where it's in factored form. So let's say what we have is something like f of x is equal to negative 2x minus 3 squared times 1 minus x cubed. So the important things about this will be determined from the leading term. So the leading term here, we just ignore within each factor everything that is not the leading term. So from this factor, yep, still negative. So from this factor, there are no other terms, so there's only that one. However, from this factor, we do have a term to ignore. We don't care about that minus 3. Over here, we ignore the 1, but we respect the negative x. That's part of the coefficient of the x. You respect the coefficients and the powers of the x. You just ignore the lower terms. So that's going to be negative 2, 1, 2, 3. Oops, that's a cubed, obviously, not x to the x. That's crazy. So 2x, x, x, and then this is going to be 3 copies of negative x, which is going to be, better just be careful here, times x squared, and then times, it's going to be negative x, negative x, negative x, so the result will be negative x cubed, and that's going to make a total of positive 2 x to the power of 6. 1, 2, 3, 4, 5, 6 x's. Which gives you up and up on the right and left. So this direction is right and up. This direction is left and down. So that means f of x is going to infinity as x goes to infinity. F of x is also going to infinity as x goes to negative infinity. Sometimes you can, if they're both going the same way like this, you can collapse it and just say plus minus infinity here, but let's not get too risky. And then for the last one, let's take something like this. H of x is equal to 1 minus x to the power of 9. So 1 minus x to the power of 9. Well, in the leading term, calculation, we don't care about that 1. All we care about is the negative x to the 9th, which is the same as just negative x to the 9th. So because it's negative and odd, that tells us that it's going to be an upside down version of a cubic. So it's going to be up on the left, down on the right. So left, up, down, right, down. So that tells us, if your function is ever called something other than f, you should say that in your long-run behavior. So it should be g of x and g of x up in part b. And similarly right here, should be h of x. It's going to negative infinity as x goes to infinity, so it's down and right. And h of x goes to positive infinity as x goes to negative infinity. So that's going up as x goes left. Okay, so that's the long-run behavior of a polynomial. Now, for some short-term behavior, we can talk about such things as the intercepts. The graph of a polynomial will intercept the y-axis when x equals 0. So in other words, to find the y-intercept, set x equal to 0. And similarly, the graph will intercept the x-axis when any of its factors is 0. So for the x-intercepts, set each factor to 0 and solve. Now, intercepts refer to points where the graph crosses one of these two axes, either the x-axis or the y-axis. So an intercept is a point where the graph crosses one of the coordinate axes. So the format of your answers here should be, for a y-intercept, since it's a point, you should be giving both coordinates of the point, and the x-coordinate is guaranteed to always be 0, and as for the y-coordinate, it'll be whatever it's going to be. And for the x-intercepts, their format will be something and then 0 for y. So some x value and then 0 for y. Now let's try this. So as an example, find the intercepts of the function. Let's start with one that is nice and fully factored out. We could have f of x equals, and we could have 3 times 2 minus x times x plus 3 plus times x minus 1. So here, let's start by finding the y-intercept. Y-intercept you get when you plug in x equals 0. So f of 0. So you just put zeros in wherever there was an x. So 2 minus 0. 0 plus 3. 0 minus 1. And that's going to equal 3 times 2 times 3 is going to be 18 times negative 1 is negative 18. So that's going to be a y-intercept with an x-coordinate of 0, a y-coordinate of negative 18. Now as far as the x-intercepts go, that's where each factor gets set equal to 0. And if the factor doesn't have an x, then you don't have to worry about it. But if it does, so we're going to have 2 minus x equals 0, which is going to lead us to x equals 2. We're going to have x plus 3 equals 0, which leads us to x equals negative 3. We're going to have x minus 1 equals 0, which leads us to x equals 1. So then the different coordinates here we're talking about here are going to be 2, 0. We're going to have negative 3, 0. And we're going to have 1, 0. Okay, now let's try one like this. G of t is equal to t cubed minus 8. So here it's not written in factored form, but we're going to treat this just like one factor basically. So for the y-intercept, you put the input to 0. Here it's going to be actually t, which equals 0. So g of 0 equals 0 cubed minus 8. So that's going to give you the coordinates of 0, negative 8. Now for the x-intercepts, basically you can just treat that whole thing as one factor. T cubed minus 8 equals 0, and try to solve that for the t. So t cubed is equal to 8. I'm just adding 8 to both sides. Take the cube root of both sides. And it doesn't need a plus minus because it's odd. And that gives you just t equals 2. And that's the only x-intercept. So then that's going to be 2, comma, 0. And then last of these, let's go with h of x equals x times x squared minus 7x plus 10. Now here, our approach is still the same for the y-intercept as it always is. You just set the input equal to 0. So h of 0 is going to equal 0 times 0 minus 0 plus 10. Well, 0 times 10 is equal to 0, which gives you 0, comma 0. Now for the x-intercepts, we have a couple of factors that involve the x. One of them is just x. So that's that same point again, 0, comma 0. But we also have x squared minus 7x plus 10 equals 0. But this can be factored to x minus 5 and x minus 2 equals 0, which then leads us to x equals 5. I should do that. X minus 5 equals 0, which means x equals 5. Or x minus 2 equals 0, which leads to x equals 2. So that gives us now the other two x-intercepts of 5, comma 0. So the x value is 5, y value is 0, and 2, comma 0. Oops, sorry. All right. Now the last thing we're going to talk about on the graph of a polynomial function is just its general appearance. So we have a combination of little factors, little terms, each of which looks kind of like a little parabola or cubic. And so when we add them all together, we're going to end up with a wiggly graph that doesn't have any corners and just wiggles a certain number of times. So, graphs. Graphs of polynomials. So first off, the overall shape is going to be smooth and wiggly. So graphs of polynomials. So polynomial functions have smooth, continuous graphs. So they have no corners, no gaps, no vertical asymptotes, they just look like this. Now, A couple of things about the graphs of polynomials that depend on the degree would be the number of crossings it's allowed and the number of times it's allowed to change direction. So the number, so let's see, if the degree is n, the graph can have at most n X intercepts and at most n minus 1 turning points. So where the graph changes direction. So here, for example, we would see 1, 2, 3, 4, 5 x-intercepts, and 1, 2, 3, 4 turning points. So we can conclude that the smallest the degree of this could possibly be is 5. Now notice it says at most that, which means there might be fewer than the allotted number. You can come in under budget, and that's fine. Now let's see what this would look like for you as an example. So is the following a polynomial? And if so, what's its least possible degree? Alright, so for the first graph, let's take something like this. So, quick answer, no, this is not a polynomial, it has a corner. No. Has a corner. So we know actually that this would look like a transformation of the absolute value. Namely, it would have a vertical reflection and it would be shifted up and to the right. Now let's see one where it could. So the shape of this one is plausible for a polynomial. It's smooth, it's wiggly, it doesn't have any corners, doesn't have any discontinuities, it doesn't have any vertical asymptotes, it just wiggles its way for a while, then it ends up going up or down. So yes, and then you can look at the x-intercepts and look at the turning points to make a decision about the possible degree. So it has 3 x-intercepts, but you'll notice 1, 2, 3 turning points. So you might have thought that it was going to have a degree of 3, but the 3 turning points would mean that the degree has to be at least 4. Oh, sorry, 5. Sorry. 4 turning points. 4 turning points. So that means the degree has to be at least 5. It always has one higher degree, at least, than its number of turning points. Now, what about a graph like this? So here, we can just close the book on this one. No. There's a vertical asymptote. That's the kind of thing you could see in a power function, but not a polynomial. Now, lastly, let's take a nice simple one. So it's smooth, it's continuous, no corners, no vertical asymptotes. Looks good. Yes. And because of its 3 X intercepts and its 2 turning points, you could say the degree is at least 3. And that's as much as we can say right now about 5.2. We'll pick this back up. There's more to cover in 5.2 and then in 5.3 next time. So, till then, bye.